Welcome to the last video for chapter 12. So this is topic 67. I'm going to go over with you questions 80 and 82. You should definitely look at questions 79 and 81, think about them, and then look up the answer in the solutions manual to understand what makes water so unique. Chapter 12 slides 11 has a great picture of the phase diagram of a typical substance versus water. This is going to be my sad little drawings. If you can pull that up and look at that, that would be fantastic. So what is going on here is I'm showing you a phase diagram of something that's typical. Okay, so a typical substance, as you go across at a given pressure, right, you're going to go solid to liquid to gas. And notice that this solid liquid transition line has a positive slope. Okay, so what this means is that the solid is more dense. So if I were to have a liquid and I were to increase the pressure, so let's say I'm here, right? I have a liquid, I increase the pressure, it would switch to the solid because the solid is more dense. Okay. That means that for most substances, if you have the liquid and then you form some solid, it would sink, right? Because generally solids are more dense than liquids. However, water is different. So again, if you go across, say, at 1 atmosphere, right, you would notice that it melts at 0 degrees Celsius, it boils at 100 degrees Celsius. So here's our solid, liquid, and our gas. What we see instead here with water that's weird is the slope of the solid liquid line is negative. This means that when you form solid water, right, or ice, it actually floats in the solution. So this is really different. If you have a liquid water and you increase the pressure, it will actually form the what am I trying to say? If you're relatively near the melting point, you can actually have a solid change to the liquid by increasing the pressure. So this is the opposite of what you usually have. So increased pressure generally favors going to the more dense solid, whereas in water, increased pressure actually is going to favor going to the liquid, which is just weird. Okay. So keep that in mind. It's the slope of that line that's different. It's the density of the solid that's unique. So if we look at question number 80, it's asking us, water is a good solvent for many substances. What is the molecular basis for this property and why is it significant? So I'm actually going to read you the answer. So water has a really high polarity. It allows it to dissolve many other polar and ionic compounds, and it even can dissolve certain nonpolar gases like oxygen and carbon dioxide because it induces a dipole into these molecules. Consequently, water is the main solvent in living organisms. It transports nutrients and other important compounds throughout the body. Water is also the main solvent in the environment. It allows aquatic animals, for example, to survive by breathing the dissolved oxygen, and then allows aquatic plants to survive by using dissolved carbon dioxide for photosynthesis. So that's interesting that water plays such an important role as a solvent, not only in chemistry, but in biology. And then let me go ahead and read the question answer for 82. And then, like I said, you should look at 79 and 81. 82, how is the density of solid water compared to that of liquid atypical among substances? And why is that significant? Well, the significant difference that we see in the phase diagram of water is that you have that fusion, that solid liquid curve for water having a negative slope. That curve in the phase diagram for most substances would have a positive slope because if you increase the pressure, it favors the denser phase, which is normally the solid for most materials. But the negative slope in the phase diagram of water between the solid and the liquid, what they call that fusion curve, means that ice is actually less dense than liquid, which you know, right? Ice floats. And normally solids sink in liquids for other substances. So a frozen layer of ice at the surface of, for example, the ocean or a winter lake actually ends up insulating the water from further freezing. Whereas if it acted like a normal substance, the ice layer would sink and it would actually kill the bottom dwelling aquatic life, and it might even allow the lake to freeze solid, virtually eliminating all the life in that body of water. So that's what's really weird about the density. You see it in this negative slope, and you see it then in the physical manifestation of ice floating. And so this really has big effects on our whole planet because so much of it is water. So be sure to check out section 12.9 about the uniqueness of water.